Afternoon, everyone. This is the relearning for the law of conservation of energy. This is standard KPE.b.1. It was the second standard on the most recent test. Explain the relationship between kinetic and potential energy as conserved. Again, these two energies, as well as thermal, can be transformed. They can change form, but they cannot be created or destroyed. So there's a few things on here that you may or may not have a spot on your worksheet to put. If there is a spot, please just follow along and put it in there. If there's not a spot, it's just extra information. The first thing we need to know is that energy is the ability to do work, and the law of conservation of energy says that the total amount of energy in the whole universe does not change. But it's always moving, it's always changing. So the law of conservation of energy is the energy cannot be created or destroyed, but it can be transformed from one form to another. Again, if you need to pause the video at any point, you can go ahead and stop. Key here, when we're looking at a system such as a roller coaster, the total amount isn't changing at all. Now, the two forms we spent most of our time talking about are kinetic energy, or the energy of motion. An example of something that has this type of energy would be a moving car. And the equation for this is 1/2 times mass times velocity, which we also write down as velocity squared. So the higher the mass is, or the higher the speed is, the more kinetic energy the object will have. Potential or stored energy there are a few types. We only focused on gravitational potential energy. The equation for that was potential energy equals the mass of the object times the acceleration of Earth caused by Earth's gravity, which is 9.8 meters per second squared, times the height at which it's at. So this would be the reason why something not moving has energy. So something that's on a high shelf may have a lot of energy, and it's stored because if it falls off of that high shelf, it could do work. Now again, how does this happen? Well, when we go from potential to kinetic, as something falls, gravitational potential energy, sorry, that should say gravitational, not gravitation, turns into kinetic energy. It loses height, so if we go back to our equation here, the height decreases, but the speed is going to increase. And the total amount of potential energy at the top equals the total amount of kinetic energy at the bottom. So let's take a peek at this roller coaster example that I have for us today. So if we take a look at this, I would highly recommend that your YouTube is on full screen right now. When we play it, where is the highest amount of potential energy going to be? Well, again, if we go back to our equation, when the height is highest, the potential energy is highest. And so the roller coaster will have the highest amount of potential energy when it is at the top, the highest point. Now, as the roller coaster goes, it transforms from potential to kinetic and back again. And we can step through this. So we're going to watch it. Again, work is being done. This is not happening just by accident, but this is actually demonstrating there's a chain that pulls the roller coaster up to the top. Once the roller coaster is here, the chain doesn't do any work. And all that's going to happen now, no more energy is entering the system. And it's just the total energy is as it stands. This circle represents the total energy, and no more can go in here. Right now, it's all potential. It's pink, and the velocity is 3. So you could make an argument there really should be some kinetic because of velocity, but let's ignore that. So at this point, this is almost the lowest point, and so there's basically no potential. The speed is at its highest point at 20 meters per second, and so kinetic is most of the energy is kinetic energy. There is a very little potential energy left. If we continue on, the height's going to increase. So here at this point in the circle, the height increases. And so when height increases, the potential energy increases. And so, some of that, again, the total amount can't change. So the kinetic has to decrease. If potential increases, that means kinetic has to decrease. So the speed has decreased a little bit. Remember at 2, the roller coaster was moving at 20 meters per second. Now it's only moving at 17. So when it goes higher, what should we see about our potential? Well, the potential energy should also increase, which means the kinetic energy should decrease. And that's what as it is. So the velocity here is 4. Notice, take a moment of pause. Remember, this does not include energy loss from friction. So we're ignoring thermal energy in this simulation. Now, from 4, it's going to come down here and go to 5. The height is decreasing, which we should figure out that potential energy then will decrease because the height is decreasing. But again, the total can't change, so it's not just going away. It's going from the potential to the kinetic. So at the point of 5, again, this is where it's at its lowest point. If you look, 2 is just slightly higher. But at 5, it is at its lowest point as 100% kinetic. And at 6, again, its heights increase, potential energy increase, but if potential increases, kinetic has to decrease. So let's take so flip back here. So for thermal energy, remember that kinetic energy of the molecules, this is what thermal energy is. It's the kinetic energy of the molecules or of an object or substance. So in our roller coaster example, if we'd been thinking about thermal energy, it would have been the energy of the track and the wheels of the roller coaster. Friction is going to turn the kinetic energy of an object into thermal energy of the object and its surroundings. So if there was a lot of friction on the roller coaster, it would slow down, it would lose kinetic energy, and there would be a third slice that would include thermal energy, and it would be increasing the motion of the molecules. Remember, they go faster from our friction simulation, and it'll do that. So again, if we think back to our skater girl, the total amount of energy is not changing, but it is transforming from one form to another. This is from last year's test, but I thought I'd put it on here. So if the skydiver has 3,000 joules of energy, potential energy before the jump, assuming they are not moving, they have no kinetic energy. So the total energy the skydiver has is 3,000 joules. As it falls, if we go back to our slide about potential energy, as something falls, gravitational potential turns into kinetic. And so as it falls, this 3,000 joules is going to turn into kinetic. And right before they hit the ground, oh, I apologize, right before they hit the ground, all of that potential energy has turned into kinetic. And so the total amount of kinetic energy right before it hits the ground is 3,000 joules. If you're looking at your own test, there was a question like this. I thought, but I can't find it. I think if you are a Wednesday worker, it was number 20A. It was similar to 20A. If you're a Tuesday worker, that's the question I forgot to put on it. So the picture below shows a ball rolling down the hill and back up. So this is from your test. So I want to just take a minute, look at this, and see what you can do with this. At which letter would the ball have the most kinetic energy? At which letter would the ball have the most potential energy? At which letter would the ball be moving the fastest? And if there's friction, why would the ball not be able to make it back up to letter A? Okay, so remember from A to D to G, the total energy of this system is not changing. But at A, the height is high, and so the potential energy is high. A is slightly higher than G, if you look carefully. A is on this line while G is on this line. So the height is higher at A. So at number 2, at which letter would the ball have the most potential energy? That would be A, because the height is highest. When is it going to have the most kinetic? Well, it's going to have the most kinetic when there is basically no potential. And that would be at D. If you look back at our roller coaster, I'm going to just step through here to number 2. When the height is basically 0, it's going the fastest and it has all kinetic energy. At which letter would the ball be moving the fastest? Well, that would be at D. Because again, there is no more potential energy, so it's all turned into kinetic. And when kinetic is high, speed is high. Number 4, if there is friction, why would the ball not be able to make it back up to letter A? Well, it wouldn't be able to have the same amount of potential because the total amount can't change. And so if there is friction, then the ball will have lost some energy to thermal energy of both the ball and where it's rolling on. And so while the total of the system doesn't change, you can't have the same amount of potential if you have some of it as thermal. So if some of the energy is thermal energy, you can't have as much potential energy. How much kinetic energy is there at B? And this goes back to what I asked you earlier. Looking at the roller coaster has the highest amount of kinetic energy at the lowest point. And so at D, at the lowest point, that means there is no potential. And so all of this 100 joules of potential has transformed into 100 joules of kinetic energy. Number 2, the same system, meaning the 100 joules is the same. At B, if there was 70 joules of potential energy, how much kinetic energy was there? You said 30. You are correct because you have to add up the kinetic and the potential to make 100. I apologize, I should say K. So there should be 30 joules of Ke. For the same system, so still 100 joules of total energy, at letter C. At letter C, would you expect there to be more kinetic or potential energy? Now, if I'm you, I'm going to count these lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 maybe. Well, C is only here between 4 and 5. So C is less than halfway to the top. So that means that the height is less than half. And so the potential energy would be less than half. So we would expect there to be more kinetic energy. It's going to be going faster than at B. It's going to be going faster than at F. And its height is lower than B, F, G, and A. And number 4, in the same system of 100 joules, if there was 60 joules of kinetic energy at F, and 10 joules of energy had been turned into thermal energy, how much potential energy is there? And if you said 30 joules, you are correct. Ladies and gentlemen, there's more practice on your relearning sheet. Please go ahead and get that done and turned into me ASAP so you can get on track in my class again, or at least get the standard passed. Thanks very much. Hope this helped. Have a great day.